This reciprocating compressor has been boosting natural gas up to sales pressure for 70 years. That's a remarkable lifespan for a piece of equipment like this. And then maybe it isn't, when you consider the kind of maintenance and care it's received. Now, a good operator can do a lot to prolong the life and maintain the efficiency of units like this. Learning how to do that is what this module is all about. This is the first section of a 5-section module on reciprocating compressor operation. In this section, we'll take a look at a typical compressor package, including its components and subsystems. Now, before going any further, it's important to note that you should have completed the modules Reciprocating Compressor Principles and Basic Principles of Pressure and Temperature, or have had operations experience equal to the material contained in those modules. Now, if you haven't, we strongly recommend you complete those modules before studying this one. To operate a compressor efficiently, an operator must know the components and subsystems of the compressor package. So let's review those things now, using a compressor package to show you the examples of certain components. We'll start with the cylinder and piston. Here's where most of the action occurs in a reciprocating compressor. In the cylinder, a trapped volume of gas is compressed by the piston, increasing the gas pressure. The gas is then discharged, and a new volume of gas is again compressed by the piston. This cycle repeats itself hundreds of times per minute. When gas is compressed, it generates heat. So to help control heat buildup and prolong cylinder life, cylinders have passages for cooling water. Keeping things cool is vitally important in operating a reciprocating compressor, because excessive heat buildup can damage equipment, resulting in lost revenue and costly repairs. So, in addition to cooling passages, most compressors have lubricant added in the cylinder walls to reduce wear from the friction generated by the back and forth motion of the piston. Now, other compressors use special material, for example Teflon, to reduce friction. To further reduce wear on the pistons and cylinders, rings are mounted in machine grooves on the piston. The primary function of these rings is to create a pressure seal that prevents gas from leaking from one side of the piston to the other. Each cylinder also contains 2 sets of valves, suction and discharge. These valves look similar, but gas travels through them in only one direction. As suggested by their names, a suction valve allows gas to enter the cylinder for compression, while the discharge valve lets the compressed gas leave the cylinder. Although there are several different types of valves, they all work on the same principle: differential pressure. Like water seeking its own level, gas will travel automatically from a high pressure to a low pressure area. So in the case of a suction valve, a lower pressure inside the cylinder and a higher pressure outside the cylinder cause the valve to open, allowing gas into the cylinder. The reverse is true for a discharge valve. The compressed higher pressure gas escapes the cylinder to a lower pressure area through the discharge valve. Moving along now to the crank end of the cylinder, we find packing that surrounds the piston rod. Constructed of rings and cups in a cage, packing is used to prevent pressurized gas from escaping to the atmosphere, or crankcase. To reduce wear, the packing may have lubrication ports, or be constructed of special materials, such as Teflon. Like the cylinder, the packing can also have cooling vents for water circulation. Within the compressor, there are two types of rods, piston and connecting. A piston rod joins the piston to the crosshead. The crosshead converts the rotary motion of the crankshaft into the back and forth motion of the piston. The crosshead must be held in very close tolerance to the crosshead guides to ensure horizontal, level motion of the piston. Slippers, shoes, and shims are used to keep this close tolerance. Here again, lubrication is important, and crosshead slippers are lubricated from the crankcase or through ports. The connecting rod joins the crosshead to the crankshaft, transferring the circular motion of the crankshaft to the horizontal movement of the crosshead. The frame of the compressor houses the crankshaft and provides central support for the crosshead guides and the cylinders. Now let's talk about bearings. Compressors have main bearings and rod bearings. Main bearings support the crankshaft at the center line of the frame. Rod bearings, located at each end of the connecting rod, allow the rod to rotate smoothly with the motion of the crankshaft. Both main and rod bearings are types of sleeve bearings. Once again, lubrication is vital. In fact, lubrication must be continuous to keep friction minimized. Between the crosshead bed section and the cylinder is the distance piece. This is where you'll find the wiper rings and pressure packing. The distance piece prevents any process gas from leaking into the crankcase and provides a way to vent any leaking gas away from the compressor. In order to prevent lubricant in the crankcase from entering the cylinder, wiper rings are placed between the distance piece and the crosshead bed section. The collected lubricant is drained from the distance piece to a sump line, while the pressure packing on the crank end of the cylinder seals gas in the cylinder. Before gas enters the compressor, it goes through a scrubber like this one. Liquids and contaminants are separated from the gas stream inside the scrubber. They drop to the bottom of the scrubber and must be emptied. Now, if the liquids and contaminants are not periodically dumped, they could pass into the equipment, causing compressor damage. These are called pulsation bottles. They are used to reduce pulsation in gas pressure caused by the reciprocating movement of the piston. The bottles, mounted on the suction and discharge sides of the cylinder, help reduce gas pressure fluctuations through the compressor, lowering the damage and wear caused by excessive vibration. As we mentioned earlier, gas temperature increases as gas is compressed. So to control gas temperature, discharged gas is passed through a cooler to remove some of the heat. Usually it's an aerial cooler with separate passages for compressed gas, water, and lubrication. Now, part of the cooler may have passages for water to cool the prime mover and compressor cylinders. In addition to the suction and discharge valves, there are a lot of other types of valves in the inlet and outlet piping of a compressor. Check valves ensure that gas flows in one direction only. Relief valves prevent overpressuring of the compressor and piping. Vent valves allow depressuring of a single compressor cylinder or the complete compressor package. And recycle valves allow the same gas to flow through the unit a second time. The last of the main components for a reciprocating compressor is the control panel. It is the central location for switches, gauges, and indicators. If there is no central control panel, the compressor and prime mover must be controlled and monitored remotely or with separate controls around the package. Those are the main components of the reciprocating compressor itself. Now let's take a look at the prime mover. In today's oil and gas operations, there are two kinds of prime movers used with reciprocating compressors: internal combustion engines and electric motors. Electric motors, coupled to the compressor crankshaft, are being used more often these days to eliminate hazardous air emissions and to cut down on maintenance and fuel costs. Internal combustion engines, however, are still the most common prime movers for reciprocating compressors. They are either a 2-cycle or 4-cycle engine. Engines for compressor packages are considered either integrated or separable. Integrated engines are a part of the compressor frame and cannot be separated from the compressor package. They operate in the 250 to 350 RPM range. Separable engines are connected to the compressor with a coupling and can be attached to any load. They usually run between 600 and 1,000 RPMs. The ignition system on a prime mover performs a couple of different functions. First, it provides electric current for ignition. It also gives spark for combustion in prime mover cylinders. Finally, it is an integral part of the safety shutdown of the compressor. When the control system senses an unsafe condition on the compressor package, the ignition system will automatically trigger a shutdown. There are two types of ignition systems, magneto and electronic. Magneto systems are typically found on older compressor packages, while the newer ones have electronic systems. And that brings us to the end of Section 1. So far we've covered the components and prime movers for compressor packages.